Good evening, everyone. I'm James Dietrich. I'm the chair of the NEO-ACM, and I want to welcome you to our remote talk, Telling Robot Stories, by our speaker, Cameron Hughes. NEO-ACM is the Northeastern Ohio Association for Computing Machinery, the co-sponsor of this event with George Mason University's African American STEM Speaker Series. NEO-ACM is a professional chapter of the International ACM, the world's largest educational and scientific computing society that advances computing as a science and as a profession. NEO-ACM is based in Youngstown, Ohio, and for over 10 years of our existence, we meet regularly to discuss diverse topics and function as an intellectual and geographical node of activity for both ACM members, the computing community, and the general public by offering seminars, lectures, forums, and the opportunity to meet peers and experts from many disciplines. I want to mention that June 4th, the NEO-ACM will be sponsoring a talk by the Free Software Foundation. For this presentation, the FSF Executive Director, Zoe Koyman, and the FSF Campaign Manager, Greg Farrow, will give an introduction to the concept of software freedom and its philosophical underpinnings, as well as the role it plays in ensuring software users around the globe remain in control of their computing. We'll be announcing this presentation soon through our meetup. Hope you look out for it. All right, Trevor, take it away.
Thank you, Jim. Good evening, everyone. My name is Trevor Watkins, Teaching and Outreach Librarian on the Teaching and Learning team at George Mason University Libraries. Again, I'd like to thank everyone for coming this evening for the second talk and the final talk for the African American in STEM Speaker Series for this current semester. And again, it's a great partnership between George Mason University Libraries and NEO-ACM. To reiterate, the goal of this series is to highlight past and present contributions from African Americans in science, technology, engineering, and mathematics, from practitioners, innovators, authors, inventors, and educators in these fields, with a focus on individuals you may not have, have heard of. In the fall, we actually probably in September, we already have one mathematician and one chemist and one engineer. So we will send emails to everyone who's registered to let you know exactly those dates for those upcoming talks. So now I'm going to talk about our speaker for this evening, who's Cameron Hughes. He is a software epistemologist at Ctest Laboratories, where he is working on AIM, which is the Alternative Intelligence for Machines, and AIR, which is Alternative Intelligence for Robot Technologies, as well as the co-developer of the AI Cosmology, a software visualization system about the history of artificial intelligence. Cameron is the lead AI engineer for the Knowledge Group at Advanced Software Construction, a builder of intelligent robot controllers and software-based knowledge components. Cameron is a member of the advisory board for the NREF, National Robotics Education Foundation, and co-director of the Oak Hill Robotics Makerspace. He is the co-author of Build Your Own Team of Robots, published by McGraw-Hill Tab Electronics in 2013. And of course, Robot Programming, a Guide to Controlling Autonomous Robots, published by Q Publishing in May 2016. He is the co-author of many books and blogs on artificial intelligence, as well as books on multi-core and multi-threaded programming, Linux rapid application development as well, and of course, object-oriented programming and parallel programming in C++. He received an MCIS, which is the Masters of Computing and Information Systems from Youngstown State University in 2008. So everyone, please welcome Cameron Hughes.
I first want to say thanks for the George Mason for having me a part of the STEM Speakers Series. It is certainly my pleasure. And I also want to specifically thank you, Trevor, for such a nice introduction. It's a bit much. I just consider myself really, at the end of the day, a computer programmer. The presentation that the short talk that I'm going to give today is basically going to be from a programmer and a software developer point of view. So for those out in the audience listening, don't be deterred by any of those titles, and in any of the, don't be put off, because I am basically, I spend most of my time writing computer programs and software, doing testing, and messing around with the operating system, that kind of stuff. But because we're going to discuss some fairly complicated things today, in about 50 minutes, I have to oversimplify some of the concepts in order to leave enough time for questions and discussions at the end. There's a lot going on here. We've got artificial intelligence, autonomous robots, ethical and moral computing, the obligation of software engineers. There's a lot that I'm going to try to cover in 50 minutes. And each of those things really, they could take an entire college semester or maybe even an entire YouTube channel just to discuss those things. So the fact that we're going to be talking about them in this short span of time lets you know how much simplification is going to go on. But I want to present, I'm going to try to present a narrative that will connect the software development process to some of these topics, the artificial intelligence and the moral obligation of software engineers. And so, it's abbreviated. And if after the talk you feel like you wish I would have dealt with this topic or that topic a little bit more, that's very understandable. We can only do so much in this time frame. But today's talk is really meant to convey two main ideas and a recommendation. And if everybody walks away with an understanding of those two ideas, for my part, I'm going to feel mission accomplished. The first idea is that the consequences for a task that we want a computer system to perform, it can and must be understood to the fullest extent possible before we program the computer system to perform that task. A lot of times, and especially in this day and age, we kind of throw the program out, see what happens, and we deal with the consequences after fact, in an aftermath fashion. I want to convey the idea that the consequences for a task need to be fully understood before the computer is involved. The second idea is that those that are designing and programming computer systems to perform tasks and implement public computer-based solutions, those people need to have the requisite knowledge, the processes, the tools, and the ethics necessary to effectively and reliably do the job. And so, in short, if you don't know what you're doing, I'm suggesting in this talk that you stay away from this enterprise until you do know. And that may sound kind of harsh, but I'm really going to make my case today from the position of maybe 2.5 decades of being a computer programmer and a software developer, a software engineer. And so I'm coming from a very practical side of things, right? And so I want to tell you a little bit about myself. Although a lot of things are already mentioned, I just want to restate some of it. I attended a trade school in Philadelphia, and I got my first certificate in computer programming from Control Data Institute, which was a subsidiary of Control Data Corporation. I received an associate's degree in computer science from Philadelphia Community College. I got my bachelor's and my master's degree from Youngstown State University. But in addition to that, I also dropped out of a computer science PhD program from Kent State University. because me and my advisor had a difference of opinion on class attendance and completing the exercises at the end of the chapters of Russell and Norvik's textbook on artificial intelligence. For some reason, he thought that was a good idea, and I didn't. And so we didn't see eye to eye. And so didn't get very far in the PhD program, but I did make an effort. For most of my professional life, I've held the titles of programmer analyst or software engineer. And I've worked on small and large software development teams. I've written computer programs from the very, very simple to the extremely complex. I've worked in these development areas. And I don't want to mention the names of these companies because I may say something that might get me in trouble. So I don't want to. The names have been changed to protect me or the innocent. But a large computer system program data conversion, financial stock exchange, a pretty hefty electrical supply and construction company, transportation, logistics, routing, and scheduling in the special needs domain. I've worked on university student information systems and embedded autonomous systems for environmental monitoring. And somewhere along the way, I've co-authored these books with my wife, Tracy. Tracy is also a professional software developer. Currently, I'm a software epistemologist at Ctest Labs. And what that basically means, and what I basically do is I find ways to represent knowledge in discrete structures and get that knowledge into computers and into robots. Let's see here. Ctest Labs, this is just a little bit about the what the lab does. Basically it's a lab that's dedicated to environmental monitoring, and we're using computational epistemology to program the robots. We have underwater robots that we're working with that monitor lakes in the Ohio area. We support and promote AI literary citizen science. We're working on a system that will let the folks in the Ohio, the Northeast Ohio area, know about the safety of the neighborhood parks and rivers. So that's a little bit about what the research that we're doing at Ctest Laboratories. So to kind of get my talk started off, I want to talk about some of the software development issues that we're facing right now in the United States and in many countries around the world. I'm going to mention briefly 3 or 4 horrific tragedies in different domains, different areas. And the thing that those tragedies all have in common is that they were driven in large part by computer systems that were built using machine learning techniques, data mining techniques, predictive analytics, big data, and other artificial intelligence and automation strategies. The first one is it's the Dutch government. And we had a situation where in 2021, the Dutch government had to resign amid a scandal in which a tax audit and fraud surveillance system erroneously accused more than 26,000 families of committing fraud. The system encoding of government policy caused any minor inconsistency or discrepancy between the data or any failure to sign one of the pages of a form to be classified as fraudulent. The government required those families to return to the state huge sums of money pertaining not only to the period in which the alleged fraud was committed, but up to 5 years prior to when that alleged fraud was committed. The system also automatically flagged people who had dual citizenship as fraud suspects. Most of the families erroneously accused were lower class immigrant families. And this draconian way of locating cases and collecting debts led many families to considerable financial difficulties and some even declaring bankruptcy. And so this is like an example. This is a pretty public example of an AI system failure. Let's see. In addition to this, we have the concept of predictive policing and pre-crime algorithms, right? And predictive policing is just what it sounds like. It uses algorithms, data mining, and machine learning techniques that are designed to predict when people are likely to commit crimes and who is likely to commit the crimes. And sometimes it attempts to make predictions before the people commit crimes. Predictive policing also tries to anticipate who might be victims of crime. So, if any of you saw the movie Minority Report, this might bring some of that to mind. This is real. We have ICE, it uses predictive policing. I have an example of the New Orleans Police Department working in conjunction with the Planeteer systems. They use this predictive policing tool to comb through a lot of social media data and criminal history to predict the likelihood that a given individual will commit a crime. And in working in secret, the New Orleans Police Department, all the way back in 2012, they used the system against gang members and the groups called the 39ers. There's one famous guy, Easy Evans Lewis. He was one of the targets of some of this predictive policing. And at trial, they were able to produce 60,000 pages that had been secretly collected on this individual. So, we might want to think about this. Some of the people that are subject to this, these predictive policing, this has been used in many places in the United States. They've been found innocent, And so one other case, I guess here, we're using these AI systems, these data mining systems to do fraud prevention. We got 40 states in the United States that use machine learning automatic algorithms to help prevent fraud in the safety net programs that are originally designed to help the poor. They look at food stamp programs and looking at unemployment insurance claims. And so supposedly they're looking at welfare benefit programs. I want to highlight something that happened in Michigan, and I guess that's important because I was born in Michigan. And so this particular case, is kind of close to home. In Michigan, they had a $47 million fraud detection system adopted in 2013, and it made roughly 48,000 fraud accusations against unemployment insurance recipients. This was a 5-fold increase over the prior system that they had. This system made these accusations without any human intervention. The system also was so automated, it had, in the name of the state, demanded repayments plus interest and civil penalties of up to 4 times the alleged amount owed. To collect the repayments, some of these payments, I might note, was as high as $187,000. To collect these payments, an automated system engaged in state garnished wages. It levied bank accounts. It intercepted tax refunds. And the financial stress on the accused resulted in evictions, divorces. It destroys credit scores, homelessness. It created homelessness. It caused bankruptcies and in a few cases, suicide. As it turns out, the state review determined that 91 to 93% of the fraud detections were wrong. So after public outcry, out of the 48,000 accusations, 44,000 of the cases were found to have committed no fraud. So that's one of these things that just kind of jumps out at me. And again, the thing that ties these cases together is the fact that underlying them, they have big data technologies, they have machine learning technologies, they have AI technologies involved. And these things are all a function of the software development lifecycle. I want to just bring one more case that a lot of people in the United States are familiar with. The Obamacare website failure, the 2013 launch. Some say, $500,000 in contracts were mismanaged. In that situation, it was largely, most of the debacle was blamed on the website, but I want to tell you, there was a lot more than just a website involved in that system. There was a very big website presence, but the system also had a lot of back-end technology involved. The website was developed with multiple contractors. It had front-end and back-end functions. The site also needed to be integrated with insurance companies and needed to be integrated with IRS servers and needed to be integrated with Homeland Security servers and the Department of Veteran Affairs. All of these systems had, there were legacy systems, in some cases mainframes, many different kinds of languages. There was a failure in error communication between these systems. You would have errors that were created on the server side, the backend side, and there was no representation for those errors in the website. And so the website components didn't know what was going on in the back end. And then the back end, in many, many cases, was not aware of errors going on the front end. And so you had a big time error communication, just a snafu. And then you had, in a lot of cases, agile software development approaches to the front end development. That was a big, big deal. And that agile development, which at the time of 2013, agile was in its heyday. It left behind a site that was heavy with JavaScript, CSS smothered with small coding errors that became particularly troublesome when users faced bottlenecks in traffic. There were frequent typos throughout the code. And all of that just ended up being an embarrassment. And it really indicated that there was a very troubled development process. In addition to using the agile software development methodology, some of the technologies were involved in this very large scale deployment. NoSQL database technology was used, and the NoSQL is one of the darlings of the agile community. It's very good technology. I use it, but at that time, it was untested, or at least not tested in very large scale, robust type applications. And so because it was not so true and tried and not very well known, it was hard to find true and tried experts to work with the NoSQL databases. And so you had all kinds of integration problems. And because the technology was new, you had folks involved, in some of these contractors that were really unexperienced or very little experience with large-scale data processing. And so there was an issue in the Affordable Care Act that had a lot to do with not only the AI components that were involved, and there were expert systems technology involved, there were recommender systems technology involved. Not only was it the AI type of technology involved, the Affordable Care Act was a showcase for the agile software development methodology. So I want to bring us to that, and that brings us to Agile. What is Agile software development? It is one of the ubiquitous prevailing approaches to software development and deployment in use today. And it's not just in the United States, it's being used in many countries around the world. You can find all kinds of industries of all sizes that have one form or another of agile software development methodology. It's important to bring up those methodologies because the software systems that I mentioned that failed, we didn't wave a wand to get those systems. There was a process that was in place to build those systems, the systems that we're going to be using in the future. A lot of these artificial intelligence systems, automated artificial intelligence systems, we're going to use nationally and internationally. We're going to use the agile software development method. And so it's my opinion as a developer, a software engineer, that if there is a problem with the software, and then when you have software failures, one of the things that you look at is the methodology that was used to build the software. So it's not that I'm picking on Agile today. You're going to see it in the slides a couple times. It's the fact that that is the prevailing and one of the most popular approaches to software development today. You know, different variations, scrumming, extreme programming. And it has a few different variations, but they all fall under the big umbrella of Agile. And so they're getting my attention today. And so let's kind of look at what's going on here. The Agile has some basic principles from the Agile Manifesto. You can find this manifesto, by the way, at agilemanifesto.org. So if you want to dig deeper into that website gives you a pretty good indication of what Agile is all about. I just want to highlight their top three principles here. They stated our highest priority is to satisfy the customer through early and continuous delivery of valuable software. They welcome changes in requirements, even late in development. Agile processes harness change for the customer's competitive advantage. And one of their top three principles is to deliver working software frequently from a couple of weeks to a couple of months, with a preference to the shorter time scale. And so they make no secret to what they're really about. And I just have cited the top three here. There are more principles to the Agile Manifesto. And again, like I said, if you're really interested in that, please visit the Agile Manifesto site. There are a lot of developers, some may be in the audience today, that are using one version of the Agile Manifesto, but they've never actually seen the Agile development model, but they've never actually seen the manifesto, or they don't know what it says, or they don't know what the principles are. I would encourage you to take a few minutes and check those out. And now the manifesto, in addition to the principles, they really give you what their major guidelines are. They have 4 major guidelines. And they say that what they value are individuals' interactions over processes and tools. That's a good thing. Working software over comprehensive documentation. They value customer collaboration over contract negotiation. Responding to change over following a plan. That is, while there is value for the items on the left, right? We value customer collaboration. We also value, things on the right. We also value things on the left more. So it's not like they don't value comprehensive documentation or following plans or contract negotiation. It's just that they value responding to change, customer collaboration, working software, and individual interactions. They value that stuff more. So if you can understand what goes on. So here's what happens. We had the founders of the Agile Manifesto went off, and they had a 2-day holiday at a ski resort where they figured all of this stuff out. They got a bunch of the folks that were into these lightweight development processes together, the extreme programming folks and the adaptive programming folks, and the various different lightweight approaches to software development. They got together, had a powwow in one February I believe it was in 2001, not sure exactly the start date. But after those 2 days, they came up with this manifesto and they posted it, and that kind of became the gospel of the Agile software development methodology. And so that's what's in writing. But some of you may remember, most of you should remember, or I've seen this scenario where you start out with telling something, and I ran into this when I was in middle school. You would whisper something into someone's ear on one side of the classroom, and by the time it got to the other side of the classroom, it was something radically different than what it started out to be. Here, we have Big Sam got a new fast mini Mac, starts out on one side, and by the time it gets to the other side, Sam ate too many Big Macs too fast, right? And that's kind of what happened with the Agile Manifesto. When you look at the Agile Manifesto and its set of principles on paper, it's okay. It's not that there's anything wrong with it if you just look at it, the letter of what's been written down. Or if you have the opportunity to listen to some of the progenitors talk about what their principles and goals were. If you get that aspect of it, you may be okay. But what has happened in the real world to the programmers and engineers that I've run into, and the development shops and the development teams that I've had to encounter in the last 10, 12 years, what has happened in the real world is they hear something very different than what was written. Okay, whereas the manifesto talks about favoring customer interaction and these kind of things, but also valuing documentation and valuing quality. They don't get all of that. In translation, it turns out to be something different. What actually got heard by the corporate developers and the corporations and the techies, and I'm saying this from my interaction with many boots on the ground, so to speak, folks that actually develop software, they believe that only a minimum documentation is necessary. Their focus is all about speed and hurry up. There's a big focus on that. There's a continuous spur of the moment. Change is good. The more change, the better. The more impromptu, the better. The faster it comes, the better. They also believe, just as a matter of course, that formal, traditional, heavyweight software development methodologies are bad. Things like the spiral methodology, incremental rapid prototyping, they think those are bad technologies. And you don't want to mention waterfall because, you will be laughed out of any kind of agile environment. They believe those things are bad. They also believe that the buddy system can't be wrong. As long as we have two people, we've got a pair of folks working on this, we're in good shape. And the customer is always right. There's, and I want you to hang on to that last point there. We get trained on that here in the United States for sure. The customer is always right. And as developers and software engineers, our customer, the people that are paying us to develop and deploy software, we typically just accept whatever directive we receive from them as being correct and as being right. Okay, so this is what gets translated. Although the original progenitors of the Agile Manifesto did not say these things, this is how it got translated by the time it got into the wild. And I'm giving this from just personal experience. I haven't taken any surveys, or I'm not privy to any national counts or anything. I'm really speaking from what I've seen in with my own eyes and heard with my own ears. But when you look at the agile software development, what could be wrong? What's wrong with early continuous delivery? What could be wrong with that? That's a good thing. Welcoming requirements, changes in the late development. Hey, how could you go wrong with that? Delivering software frequently, maybe within 2 weeks. And in some cases, if you can get it done faster than 2 weeks, the customer is even happy. Who could argue with those kind of goals? harnessing change for the customer's competitive advantage, right? These are all part of the mantras for the agile software development and these lightweight methods. And from a business point of view, if you're the business owner or the customer, the person that's requesting the development, this is all good news. You're going to get your software early. You'll be able to make changes in the requirements late into the development process. Maybe 2 weeks or less as far as development time. Wow, that's a good deal. And then if we can get that change in there and make sure that I keep my competitive advantage, well, what's not to love? And this is really the appeal and how the agile development process entices the software development enterprise and entices many, many corporations in the United States and actually around the world. And so, in order to really explain what I need to explain, I want to get to a basic definition here. And I apologize to all of those of you out there that have PhDs and master's degrees and computer program, that are very well educated, and you already know what a computer program is. And so some of this might seem that I'm talking down, but please forgive me. I don't mean to talk down anyone. I just really want to put everybody on the same page. Computer program is a set of instructions written in a language the computer can understand. It represents a task the computer is to perform, okay? And I want to just characterize some computer programs, and I want to let you know that there's a difference between these words. Some folks might challenge me on this. I challenge you to go do your homework because I'm right. Okay, so this is a dictatorship here. An algorithm is not the same thing as a method, and it's not the same thing as a procedure, and it's not the same thing as equations, functions, and formulas. And we can characterize computer programs in one or more of these terms and executing one or more of these kinds of instructions. I want to, in the name of clarifying some of the hype out there, I put these on a slide to maybe encourage you. Hold on just a minute. Okay, I just want to make sure I'm not too far off time here. I wanted to put these on a slide to make sure that for those of you that are, have enough time and want to do the homework, they can dig into these things. You're going to find a lot of discussion about these in computer science and programming and software engineering circles, but they are different things. And a lot has to do with, how rigorous some of them are. For instance, an algorithm is unambiguous. It's guaranteed to solve the problem in a finite amount of time if given the correct input. Today, the word algorithm is thrown around to mean anything, a program, a set of rules, like the pseudocode, there are all kinds of things. I've heard people say, well, you could have a incorrect algorithm. Well, no, if it's incorrect, it's not an algorithm. It's something else. It's a procedure. Maybe it's a program. Algorithms, if given correct data, they produce the correct input, correct output, and they do so in a finite state of time. Method, some algorithms implement methods, and one might say that all algorithms are methods, but not all methods are algorithms. We could have that kind of discussion. And a method is an approach to solving a problem, and it produces, in some cases, approximations or estimations of solutions, but methods aren't always guaranteed to solve a problem. And the approximations and estimations that they produce may not always apply in every situation. They're useful. You can get a lot done with a method, but they don't have the same force or the same guarantee that an algorithm has. And a procedure is a little bit less than that. And, and we are familiar with equations, with equations, functions, and formulas. So I just want to throw a little of those vocabulary words out there, give you something to do in your free time. And so that brings us to this, the process of writing a computer program. And certainly the programs that I brought up at the beginning of this talk started out like this. This is a simplified form here. We see someone with an idea. We see someone that is going to be programming the computer. and then we see the public with an anvil waiting to drop on the public. Maybe it drops, maybe it doesn't. I guess it depends on what's going to happen with the idea and the computer developer. And this person having an idea, I really want to focus on this, and I want to share quickly something that I ran into as a developer. And maybe I'll mention Philadelphia and New Jersey without giving away the names of any companies. I was working for a large construction company that did, they built malls and large buildings and skyscrapers and these kinds of things. And I was in charge of the portion of the computer programs that were responsible for producing quotes for these jobs, that would get the materials and the vendors together and deal with the zoning and this kind of stuff. And at one point, one of the presidents of our division came to me and asked me, he had the bright idea that instead of using their top 5 sales consultants to come up with these quotes, he wanted our group to write an expert system that would automate all of this processing. And to that individual, it was a good idea. He wanted that because he felt at the mercy of the salespeople, that their senior salespeople. They dictated terms. The junior salespeople couldn't get any sales. The senior salespeople had deep business relationships and ties with many of the people who would build malls and skyscrapers. So it was really like they had a monopoly over this company, and the company wanted to be freed from these salesmen. And so their bright idea was to use artificial intelligence and automation. And what we're going to do is write a computer program, develop a system that will replace these folks. And so for this guy's point of view, I won't say at this point whether it was bad or good. I would just say it was an idea. And it was our job to translate that idea into a set of instructions that the computer could execute. And I might just make the point, emphasize at this point, it wasn't clear whether that idea, the anvil was going to drop on the end users or not. I'm just going to, I guess, leave you in suspense here for a minute. There was a second situation that I was involved in another very large company. We were doing some logistics, routing, and planning. And we had a very big display, a video display of where vehicles are located at any given time in a city or county. And on this display would be the GPS information for the vehicle number, and some other, I can't say what those things are publicly, but some other information. I had a customer that thought that, instead of putting the vehicle description information in this software, they wanted to put color coding information in the software, because the software had a limited amount of storage space per vehicle, and so you could only store 3 or 4 items. And so they wanted to get rid of one of those items and put a color code in there, because the color coding would help the dispatchers schedule the vehicles better. And for some reason, the owner, the person that was paying me, thought that was a good idea. And so it was my job to translate that into a set of instructions that the computer could understand, right? And maybe the anvil dropped on the users, maybe it did not. And I'll just share one other third thing. I said earlier in my talk that I was involved in university information systems. I've actually worked with 2 or 3, actually 4 institutions of higher learning in the state of Ohio. And at least one of those institutions, I don't want to mention any names here, they thought it was a good idea to take their parking system and outsource that parking system to third-party software developers. But the parking system, in order for it to function, needed to have access to a lot of student data, and some of that student data was considered private. And for some reason, the folks that were in charge with requesting it with this bright idea thought it would be a good idea to send the private student data to these third-party developers. It turns out that the students in these at this institution were not very happy to find out about this, but I won't tell you whether the anvil dropped or not. You know, we'll see. Let's see. Let's go to the next thing. So here's what the problem is. You get the user who comes up with an idea, some new policy, or some new process, or some new procedure that they want to have the computer perform. And they come up with this idea, and it's communicated to the development group or development person or development company in some kind of way. And those folks, if you're talking in the last 10 or 12 years, it's a very highly likely that they used the agile software development methodology to that idea, that policy, that software request into a set of instructions that a computer can execute. And so what I want to point out here is that the person that came up with that idea, they come up with the idea, they pass it on, and then it's the developer's job just to make sure that idea is executed and to find out a way to get that into the computer, into the software application, into the system some kind of way. And there's no one that really takes the time to identify, verify, or validate the consequences of that new task before it's turned into computer instructions, right? No one really formally, prior to it getting to the computer at all, does any kind of formal analysis on what the consequences or the impact of that new process is going to be on the public, on the customer, what it's going to be on local, state, federal regulations, pre-existing software systems, ecosystems, the organizational policy, or the environment. And again, these are not guesses on my part. This is just stuff that I've just seen in the wild. You know, once the boss comes up with an idea, as the software developer or programming engineer, it's your idea to make it happen. It's not your idea to question or to scrutinize the boss's idea. So there's this assumption that when you're asked to do something as a software professional, you just do it and you find a way to make it happen. And the nice thing about Agile is Agile finds a way to make it happen fast. And to make it happen with requirements that come late in the process, and to make it happen with, where the customer is continuously making requests and improvements, and you just make it happen. And so Agile supports that aspect of it. Agile supports unit testing, and Agile supports acceptance testing. But Agile is not really real big on the concept of integration testing of the involved ecosystems or any kind of serious regression testing. So I want to focus on that original idea, that original software request, how and who identifies, verifies, and validates the consequences or the impacts of that idea prior to it becoming a set of instructions that a computer can execute.
And when I say no verification or validation, I'm not just referring to casual thinking about, what would be the benefits of the program, right? When I'm talking about an analysis of the consequences and the impacts prior to translating that program into code. We want to keep this in mind that a customer's idea for a new policy, a task, or process or procedure that's ultimately going to be implemented as a set of instructions for a computer to follow, it doesn't exist in a vacuum. That request is going to be part of some kind of existing scenario or situation, or it's going to create a new scenario or situation. It's going to be something that's going to affect the employees, or something that's going to affect the customers, or we're going to change how the gas pumps work at a gas station, and we want to change how things are priced. We want to give people the ability to pay for gas with their credit cards, or maybe we want to give them the ability to pay for gas or with Bitcoin. That's the new thing. Maybe we want to allow the exchange of NFTs or something to pay for transactions. So someone has some idea, and that thing is going to be tried in the context of some existing type of scenario. I had the example of one of the organization I work for. I had one of the owners, one of the vice presidents rather, request that I me and my team develop an expert system for their business. They had a scenario where they had 5 senior sales reps that were responsible for doing all of the quotes for large-scale skyscrapers. And these 5 guys kind of dominated all the sales, and they had all of the contacts, and they really called the shots when it came to developing these, coming up with quotes for the materials that are required to build a skyscraper. And so a couple of the vice presidents, mainly my report, he didn't like that. He didn't like the fact that these 5 senior salesmen were in control of basically his company. And so what he wanted to have done was a computer program, or a piece of software that could produce the quotes at the same expert level as those 5 senior guys that had been coming up with these quotes for 30 or 40 years. And his plan was that if we could just get all of this into software, right, he would no longer be at the mercy of these 5 salesmen, and he could assign these contracts to more junior salesmen, and spread the wealth around. The other 5 salesmen also took very big commissions, so it left less profit for everybody. And so he wanted to rectify that situation, and in his mind, the solution was to produce a computer program that could have the same performance as these 5 high-quality salesmen. And so he only saw the positive aspects of what that would do. He didn't consider what the negative consequences of that scenario would be. And he didn't expect me to look for any negative consequences. He expected me and my team to just execute his requests. And so that's an example. He wanted to put automation in place to replace senior salesmen. And he wasn't really concerned of what would be the long-term impact of that kind of automation on his business, on his employees, on the senior salesmen, on the junior salesmen. He only had the goal in mind of getting control back of his company, so to speak. And so when I say that every new policy or task or procedure happens in the context of some kind of scenario situation, that's what I mean. Piece of software doesn't just, is a free-floating thing. Computer systems tend to be subsystems of larger systems. They just tend to be components. They fit within another system, okay? And so all of the consequences of the customer's idea on that scenario or that situation, those consequences need to be well understood. The impact of the customer's request, the impact of the customer's bright idea needs to be well understood before it's translated into a set of instructions. And And I say all the consequences here, and obviously, the caveat is to the extent possible. Sometimes the consequences are not completely knowable, and we have to do our best. But currently, evaluating those consequences, evaluating the impact, is just simply not even it's not even a goal.
Okay, folks. Here, really, here's the long and the short of it. The request impact, the customer's request, that impact on the scenario, that's got to be thoroughly understood. We have to know how that request is going to impact that particular situation or scenario. And the fact of the matter is that understanding scenarios, that's a mathematical intensive activity. You can't truly understand a scenario situation, excuse me, without mathematical modeling. And those mathematical models, at the end of the day, have to be translated into models and languages that a computer or robot can process. And then those mathematical models, they need to be done, excuse me, really prior to actually programming the computer or robot. You don't wait till after it's over to come up with the model to understand the impact of the situation. You really try to understand that request impact prior to doing any kind of programming. Actually, that understanding should be a part of the design. And at the end of the day, we use those mathematical models to tell the robots and our other agents stories. And I'm going to get back to that stories concept later. But the real thing here is, the enterprise of understanding the impact of a customer's request, a software request, that is ultimately, that kind of analysis is ultimately a mathematically intensive process, and there's really no shortcutting that. And what happens with Agile's focus on early continuous delivery, requirements late in the development process or the design process, delivering software in 2 weeks or less if possible, and focusing on competitive advantage. When that's the focus, it rarely leaves time for the due diligence of scrutinizing the consequences or the impact of the original idea or the original software request. So that's the big, I guess that's the primary problem here. Agile has us focus on getting the thing done quick and to the customer satisfaction, and with a certain amount of haste and brevity. As the name suggests, customers happy. We work in teams. We allow input into the process, late into the development process, and everyone's happy. The problem is, though, we may be implementing a bad idea or implementing a request that ultimately is going to have negative consequences and a negative impact on the public, the users, the customers, the company policy, or negative impact on the environment. We just aren't doing enough analysis. And here's the thing. A lot of that analysis, understanding the impact of a customer's request, understanding the consequences, a lot of times there's math involved in attempting to do that. And in the United States, we're not very fond of math. In 2015, PISA Program for International Student Assessment placed the United States 38th out of 71 countries. And that's a dilemma, because thoroughly identifying and analyzing the consequences or impact on a scenario by some process or some policy or system is mathematically intensive. Okay, let's look at what do I mean? What I mean by that? Let's just take, for instance, a simple customer request. Let's say we have a customer that's getting so many applications for jobs till just sifting through the applications is a burden. So they want to use the computer technology to help filter job applications. So they want a piece of software that's going to filter applications and only include applications that have, let's say, a reliable car, applications where the applicant has 2 years applicable work experience, let's say maybe a bachelor's degree in computer science, and we want the person to be a citizen of the United States. Right? That's, there's no problem there. We don't have to worry about any kind of bias or any kind of racial or gender problems. This is just a straightforward request for software that can filter job applications. So the question is, will those 4 conditions satisfy the customer's unstated goal of finding the right employee for the job? Okay. And so we know what the real goal is. Sometimes the customer is able to state it clearly, and that's part of the strength of Agile is the process of involving the customer early and often allows us to understand what they really mean. But even for a simple request like this, mathematics is necessary to understand the consequences and impact of this request. For example, there are 2-to-n combinations of a Boolean interpretation of the conditions. In other words, what that means is just taking these 4 basic conditions. We want to know if the applicant has reliable transportation back and forth to work. We want to know if they have experience. We want to know if they have a college degree, and we want them to be a resident of the United States, a citizen of the United States. Those 4 things, if you look at their Boolean interpretation, there's 16 different kind of combinations of those things that if we're doing our jobs and really trying to satisfy the customer's goal, we'll look at 16 variations on that 4 conditions. And here's what they are. The person, like case 1, they have everything. They have the car, they have the experience, they have the college, and they're a resident. And then if you can see for the cases 2 through 16, something is missing, right? And so in the first case, the applications that meet all of those conditions, and those are the conditions that the customer explicitly stated, those applications would pass, and all the rest of these applications would fail. If a person has a car and they have the experience and they have the college degree, but they're not necessarily a citizen of the United States, we're going to pass by that person, right? You could have a situation where maybe they have case 3. They have the car, they have the experience. Maybe there's something wrong with the college, but they are a resident, so we're going to pass by those. But do we really want to pass by those? Like, let's say in the first case, the person, although they weren't a citizen of the United States, they have a permanent visa or they have a permanent green card, and they, so for all intentional purposes, they're like a citizen of the United States in terms of their longevity, their plans to be here. So it might be that the ideal person has everything, and if they have a permanent visa, a permanent green card, maybe we should consider them. Okay, what about the situation where the person doesn't have a car? That would be, let's say, that'd be case number 9. They don't have the car, but they do have the experience, they have the college, and they have the residency, or they're a United States citizen. that application might be passed over. But what if this ideal person lives across the street from the company? They don't need a car, and they can just walk across the street and be at work. And so the issue of getting back and forth, in a timely manner or reliable manner, doesn't require a car. So maybe in reality that requiring a car thing was too restrictive. If we're doing analysis on the request of the impact of the original customer's request and the original customer's idea, we have to look at things like this. And he gave us 4 conditions, and out of those 4 conditions came 16 possibilities. Well, we only know that because we're using techniques from discrete math. We're using power rules from set theory or something, right? We're using Boolean algebra. And so it's just very simple math, but it's a useful kind of math. And even for the simplest problems, to analyze the consequences and the impact, there's always going to be math involved. And that's one of the things that we hide from in this country, and we don't want to own up to. And sadly, as that problem intersects with the Agile issue, we run into a problem, because in order to really deliver quality software, true quality, reliable, fair, unbiased, environmentally safe software, there's going to be some mathematical analysis required in the design phase of the software development, and that's prior to any code being written. But we, as a country, math is not our strong suit. Okay. If I did another really kind of just a fun example, here's another simple thing. Let's say we get a robot and we want our robots, we've purchased one of these things, only 15, 20,000, not much money. Very sophisticated robot, you're using state-of-the-art artificial intelligence. And we give the robot a command to find and fetch our car keys, right? If you don't know what goes behind that kind of programming, you may not be aware of the kind of mathematics that's involved. But it's something just that simple. We aren't asking the robot to do surgery or, any kind of engineering or rocket science. We're just asking the robot to fetch the keys, find them and fetch them. I know I lost them somewhere. Go get them, Robbie. There's mathematics necessary in the robot's set of instructions to even do something as simple as find car keys. There's probability theory involved. There's distance formulas and navigation algorithms, that require trigonometry and geometry, analytic geometry in some cases. Planning a course and route through my house is, there's graph theory in there at least. The search strategies that the robot's going to use is going to be optimization things in there, because it's got to minimize time and maximize battery use. So it's going to be optimization and some calculus and, who knows, maybe some real analysis in there. Just to understand my command, robot find and fetch my car keys, to understand what that meant, right? All kinds of formal languages and mathematics goes into that. Predicate calculus, conceptual graph, among other approaches. And to know the car keys when he sees them, when it sees them. There's matrix linear algebra, inferential statistics, whole bunch of stuff, whole bunch of different kinds of mathematics goes into that, right? And it's a very, very simple thing. And I guess I want to focus on this because when you're dealing with AI, you're dealing with autonomous robots, you're dealing with smart agents, you're dealing with these kinds of technology. I don't want this particular audience, anybody in this audience, to lose sight of the fact that these are mathematically intensive concepts and technologies. And we are talking about this stuff every single day. But at the same time, as a country, we're relatively weak in the math area, which, in my experience, it does lead to weak software, does lead to faulty software, does lead to the kind of catastrophes that we talked about at the beginning of this talk. There is a reason why, at least at the software level, a lot of those catastrophes happened. And a lot of that had to do with a failure of the analysis of consequences, a failure of analysis of impact, what this software function would do. And a lot of that failure had to do with the fact that the people involved just simply didn't have the mathematical maturity or sophistication necessary to get the job done, right? And I guess I'm going to make that point and drive that point home. This stuff is serious business. And herein lies the rub, right? The talk of artificial intelligence, autonomous robots, machine learning, and ethical computers has infiltrated practically every country. We now need safe, reliable, secure, and ethical systems. But Agile is currently the prevailing software development methodology that's being used to develop many of these AI systems. And Agile fails at the point of the software requests and ecosystem integration testing. And what I mean by that is before we get to actually writing code or translating the user's request into computer instructions, before we even get there, we have not done the necessary analysis of the consequences and the impact. And that analysis of consequences of the impact is going to be a mathematically intensive thing. Programming for AI, machine learning, and autonomous robots is inherently math intensive. And the potential for AI for good to our society is boundless. The potential for AI catastrophe in society is also boundless. Our software development methodologies must be based on sound engineering, scientific method, and all the mathematics we can use. It's just my opinion, but I don't think now is the time for, profit-saving, get-it-done-quick schemes in this buddy system where, we kind of, program as we go and get it out into production. That's, I think that's hurting us in the long run. So, let me just say briefly here, and just to, I guess, drive the point home. When we hear the term artificial intelligence, I've mentioned it several times in this talk so far. What do I actually mean by artificial intelligence? I guess I will say, at Ctest Laboratories, this is how we use it, how we define it. We call it an implementation of thinking processes. Okay. Thinking machines. It's the implementation of thinking processes. So we tend not to use the term artificial intelligence much. And we try to be a little more precise in what we're saying. That's a fairly generic term. What does artificial mean and what does intelligence mean? And you put those two things together and we're really confused. So that's the definition we use at Ctest Laboratories. And another, I guess, a caveat is the fact that artificial intelligence only applies to non-human computers, right? It doesn't apply to anything else, right? And so we have to kind of keep that in mind. And so when we say thinking, we've broken the thinking process down. There's some specific operations that we focus on at Ctest Labs. The notion of deciding, calculating, counting, and estimation. The process of comparing. We look at recognizing, interpreting, deducing, inferring, abducing, generalizing, recalling, and sorting. We have very specific thinking processes that in mind when we are doing that the activity of artificial intelligence programming, and so programs that focus on these kinds of operations are implementing for us models of the thinking process. And those models can move from deterministic to non-deterministic in terms of complexity. But that's for another day. I just wanted to kind of clarify, we really translate artificial intelligence into thinking machines and thinking processes particularly. And we have a set of operations in mind when we say that. And then for machine learning, that's another term that's being bandied about these days. Machine learning is a form of automated programming where you get one set of computer instructions and proves another set of computer instructions automatically. That's without any human intervention or with very little human intervention. We get a set of instructions. It gets input into a set of algorithms and methods, and out comes a new or better set of computer instructions. And that whole automated process, we call that learning. I don't know the machine learning thing. I don't know if that's such a good name because it gives the impression of something going on with the computer program or the software that's not actually going on. Yeah, we start off with one program or set of programs, and we end up with an improved program or set of programs. But just because it's improved doesn't mean that learning has taken place. So we could argue about that. I guess the key for the business community is that it's an automated process and doesn't require manual programming. It saves money, saves time, this kind of thing.
Let me revisit for the moment the notion of telling robot stories. We call robots hardware agents and AI programs or intelligent programs or subroutines. We refer to those as software agents. And this notion of telling stories to hardware software agents, this is something that we came up with at Ctest Laboratories. And it's actually the process of describing to the hardware or software agent using some language that they can understand, some kind of computer programming language. It's the process of describing the scenario or situation that's under consideration. The domain situation, whatever it is that we are talking about, the area that we are getting ready to program a robot or a intelligent agent to deal with. That's the situation or scenario under consideration. We describe the problems that are in the scenario and the solutions that are in that scenario, and we do so using formal languages. I bring up this at this point because we've already made the point about how important mathematics is in the analysis and situation and scenario description. And I just want to draw that correlation or the connection here that the notion of telling robot stories is also a mathematical or mathematically intense process. And STORIES is an acronym that we have we came up with at Ctest Laboratories. It stands for scenarios translated into ontologies, reasoning, intentions, and epistemic situations. So it's kind of a play on words, but it does, the goal is to describe to the robot or agent, software agent or hardware agent, the complete scenario, the problem of the scenario, and the solutions that are involved in the scenario. And we do so using formal languages that hardware and software agents understand. And invariably, these languages, this is all very much a mathematical process. We use all kinds of math in this process, from discrete mathematics, model theory, category theory. Calculus is being used. There's topological reasoning, just lots of different kinds of math. So the notion of taking a real-world situation or real-world scenario and describing
the actions and events, the people, places, things, and ideas in that situation or scenario. It's a very mathematical process. And that whole thing, when you're done describing that, a lot of times we use a shortcut name. The word ontology is used to capture that kind of mathematical description. So to try to tie some of this stuff together here, the stories is a part of the analysis phase, and this analysis is done before any programming is done, before the software is developed. This is a part of analyzing that original idea, the original user's idea, the bright idea that the user has to come up with some new kind of process or procedure for computer technology, some new kind of application for computer technology. We translate that entire new idea into stories first. It's a part of that analysis, and we really don't move forward until we have clear stories to tell our hardware and software agents. And so with respect to the Agile process and some of the things we talked about earlier in the talk, our response to some of that stuff is the notion of introducing stories. Stories that will be told to the agents, and figuring out what those stories will be prior to actually coding, prior to developing the software, prior to putting the stuff, making it available to the users, developing these stories in as our part of our analysis of the situation, the scenario, developing these stories so that we can understand that impact, the idea impact. The stories help us understand the idea impact and provide a roadmap to what the real solution and what the real problems actually are before the coding process takes place. There's also the question of whether computer programs can be ethical or not. And they can, right? A set of instructions, computer programs, that set of instructions can be written using ethical and moral directives of formal languages. We use deontic logic and dosastic logic to implement ethical and moral directives inside of computer programs. And I will get into that a little bit in a minute here. But before we can talk about ethical or moral hardware and software agents, we really have to, at this point, make the case and make the point that the developer, the software designer, the software engineer, the morality and ethics involved in that process and in that position, it requires that the original idea, the customer, the organizations, the bosses, wherever the directive comes from, that original idea has to be vetted. We have to have a valid analysis that lets us know the impact of that program or process that we're getting ready to implement for computer execution. We need to know what that impact is going to be prior to writing code. So the idea that you're given a directive or a software request and it is your job as a software engineer to just get it done as quickly and efficiently and effectively as possible, and we reject that notion as your only obligation. You have an ethical and a moral obligation to make sure that that request is not going to have a negative impact on society on the environment, on the community, on the law, etc. You have a moral and ethical job to determine if that idea has been vetted. We cannot adopt the position that, well, we're just doing what we've been paid to do. There's an ethical and there's a moral onus on us to understand the impact and the repercussions of the software that we're getting ready to implement. The computer programs, that set of instructions that we're getting ready to give to the hardware software agent, there's a requirement that we understand what that impact is going to be. And the notion of that we just implement what we're being told to implement or implement what we're being paid to implement without any question, that's immoral and that's unethical at the end of the day if we don't make any considerations about the repercussions for that. And we use that stories process at Ctest Labs to address that moral and ethical prerequisite in the mathematical analysis that's required. So at the end of the day, to my software developers and software engineers out there, you need a certain degree of mathematics to even be able to effectively do your job. And I don't know what you've come across so far. I'm just saying going forward, you want to make sure that you can get as much mathematics into your toolkit as possible, because that's really the legitimate way to do analysis of a customer request, an organizational request, or wherever the request is coming from, some way to determine that the impact of that software on the community, a society, the environment. The way that's done is using mathematical modeling, and that's one of the primary ways. And taking that mathematical modeling and building prototypes and doing an analysis and evaluation from that point. We can't really skirt that responsibility as software engineers and software developers. So in terms of computer ethics and AI programs being ethical and moral, the software engineers have to be moral first. The request, the initial software request, the customer's idea has to be ethical first. It has to be moral first. There's no such thing as somehow the computer makes something that was immoral or unethical. There's no way that the computer can translate it or transform it into something that's moral or ethical. So we tell the robot stories, and we tell the robot ethical stories and moral stories to begin with. And in terms of the mathematics, I just, let me throw a few things out for homework. For those of you that are likely not familiar with some of this stuff, we have logical and mathematical languages that can be used to program ethics and belief and safety and knowledge within our computer programs. And we use these languages whenever we're really truly solving or writing computer programs that are involved in complex problem solving that interact with the public. I'm going to throw these are all, what you see listed here are various formal languages, basic mathematic structures, deontic logic and dosastic. Epistemic logic has to deal with knowledge, and belief, dosastic has to deal with belief. Deontic has to deal with the ethics and morals, temporal logic, time, predicate calculus, event calculus, situation calculus. I challenge you, or not necessarily challenge you, but for your own reading or just your own interests to update your knowledge base, take a hard look at these formal languages and what they're used for in terms of computer programming. And that'll help you get a better sense of, the kinds of, the methods and the types of models that you would need to build to make sure that you were dealing with a computer program, hardware agent or software agent that was safe for the public, that was ethical, and that these languages allow you to evaluate the ethics and morality of the software that you're getting ready to or may have been asked to implement. So, for those of you that managed to endure this talk, I want to bring it to a close with this final diagram here. Initially, we started off with the Agile process where we were given a directive, and the goal is just, get it done and get it done effectively and quickly using paired programming and etc. We want to inform that process by saying we need to come up with the correct stories and mathematical models during the analysis phase. All of those ideas, those directives, those customer requests, all that stuff needs to be vetted long before it's put into computer programs. We need to understand what the impact of those directives, the impact of those requests, the impact of the ideas that the owner, the customer, the business, the organization, the government has had in terms of implementing some of this stuff. We need to know what's going to happen before we put it in the computer. Those disasters that we talked about at the beginning of this talk, those disasters would not have happened had the proper analysis and mathematical models been considered, because you would have seen that stuff coming. And yes, it's tough, it's difficult, but we have the tools to do it. I just want to relay, just from a matter of personal experience, that those tools are mathematical tools. And there's this process of analysis is a mathematical process. It's mathematically intense. There are no shortcuts. We need as much math in our programming and software engineering toolkits as we can get, and then some. And so, just to bring this to a close, the process of getting the idea from the user, yes, we want to make users happy as software engineers. Yes, it's our goal to build software, but yes, it's also our goal to make sure that the things that we're getting ready to implement into the computer and translate into computer instructions, that those things are moral and ethical from the start. If they aren't moral and ethical going in, they won't be moral and ethical coming out, and there's going to be a disaster. And so that anvil that we talked about earlier, it tends to fall on the end users when we don't do the proper analysis. So that's what happens. So for those of you that have been waiting to know what happened with the anvil, you get hit with it again and again and again. That's what we saw at the beginning of the talk. We did just a handful of catastrophes that happened, but those catastrophes happen all the time, and far too often. And in my opinion, as a professional software engineer, the problems that I've seen again and again and again is a failure to vet the original idea. And then those that wanted to vet the original idea just simply lacked the vocabulary. They lacked the mathematical sophistication to do so. And so I guess going out, the thought that I might leave with you is that the stories that we tell our agents, our hardware agents, and our software agents, those stories need to be moral and ethical from the start before they're translated into computer programs. Thank you.
Okay, Cameron, we have George. He had raised his hand earlier. So George, if you go ahead and you can unmute yourself and ask a question, or you can type it in the chat. I don't think I see it in the chat, but you can go ahead and ask your question. Is George there? Okay.
That was really just a minor point that struck me in the larger context. And I think the larger context overrides it, but it just struck me in the discussion of the Obamacare portal, the use of NoSQL, is that NoSQL is not a guaranteed consistent database.
That's right. That's absolutely right. And something at its scope and scale of the Affordable Care Act implementation, I would have been very reticent to involve NoSQL in mission critical aspects of that. we have very robust, reliable database management systems that have stood the test of time and have taken a licking and kept on ticking. And for something as nationwide and as far-reaching and as high visibility as this project, if I were a software engineer, a programmer analyst, a computer programmer on this project, I know I would have been making a lot of noise about the selection of NoSQL, even though I use it on various projects. You have to recognize what its strengths are and what its weaknesses are. But I understand why it's used in the context of the Agile community. That's one of their darling data. That's part of the whole Agile thing. The quick, fast, and in a hurry, new, sexy. It follows a lot of the philosophy. There are, from an Agile paradigm point of view, there are a lot of good reasons that you might pick NoSQL. But from a being able to verify and validate and scale, there are a lot of good reasons that you would not pick NoSQL. So yeah, that's a good question. And so if you want to do more homework on the Affordable Care Act, and it did showcase a lot of the contractors. It showcased various aspects of the Agile development philosophy. And although it doesn't get talked about a lot, that was one of the showpieces of that system. And so you kind of, that's one of those proof of the pudding kind of things. If you were to look today, even at the Wikipedia article on Agile, you'd see that even there, they acknowledge that there's not a whole bunch of empirical support that backs up that it's a good development methodology, even though it's now used in many cases worldwide. Thank you for your question.
Thanks, George. And we have a question from Rosalind. And actually, it's an amalgamation of her question and my question. And this goes along the road of accountability and responsibility. So Rosalind asks, should just the state of Michigan be held accountable, or also the company that developed the software? And you mentioned at the beginning about the Dutch government and how they had to resign. So I'm wondering, along with Rosalind's question, who within that company, let's say the government hires some third-party company, or even if they had their in-house programmers or software engineers, who should shoulder the blame? We saw the Dutch government, they obviously had to resign, but in the state of Michigan, or maybe it's something that has to deal with, different countries has sort of different laws. But who should shoulder the blame? Should it be the boss who has the idea, or the programmer or programming team that actually implements that idea?
Right. So I'm going to just address this, just my philosophy at the moment, my personal philosophy in terms of who ultimately is to blame here. I'm going to say the software profession right now is ultimately to blame for, in all of this time, not insisting that they get a standardized body of knowledge, not insisting that we come up with an acceptable, reliable, a standardized set of software development processes, right? Not insisting on the rigor and the respect of the profession. We have largely, in my opinion, we've largely let the business community just willy-nilly dictate what the job positions are, what the job responsibilities are, what the job requirements are, what's good, what's bad, and we just kind of have gone along for the ride. And the business community, they're the ones spending the money, they're the ones paying you, but they don't have the requisite knowledge that's required in the software development process and engineering process. And so they're really in no position to define the field. But that is the case, that they have defined the field. And so when things blow up, like the way they blew up in Michigan, that was largely a function of the software development software system that was in place, the software professionals, the software industry as a whole is to blame, because it should be common knowledge at this point that you don't take an idea, a bad idea, and then take that idea and put it as a bad idea into a computer that can execute it millions and billions and trillions of times per second. That should just be common. We should have a process in place that deals with that. You know, a part of my talk was going to be the suggestion of really ramping up the preliminary design phase with things like simulation modeling and embedded subsystem processing, simulation modeling, those kinds of things that would let us answer questions about how some system is going to perform prior to putting that system in place. And we need to do that as a profession. And so I would blame us. And in the general sense of the thing, and in the practical sense of like what went down in Michigan, there were so many contracts signed and so many people violated so many things. The issue really is who would enforce the blame, right? The government officials stepped down, but you would have to be able to look into all of the people who did their jobs day to day at the government. There was a lot of misuse and abuse at that level. A lot of the people that are involved in the software development aspect, they didn't follow their jobs. So there was a lot of blame, and there could have been a lot of people being fired. A lot of people should have stepped down in a lot of ways. But just in the general case, I think the software profession, the computer science profession, I blame them, and they have only themselves to blame. I think in the long run, we're going to get our act together, and we're going to do the right thing. We're going to realize that this thing has to be regulated because the stakes are just too high. Thank you for that question.
Thanks, Cameron. And anybody want to unmute and ask a question?
Please feel free, folks. You know, I feel so bad that I wasn't able to give you a complete, formal presentation. I missed probably half, if not more, of my slides. It has some pretty good information for you all. So please feel free to ask anything that question you might have had prior when you just saw the title of this talk, and something that might have been of interest to you that you wanted to know about. Now is a good time to ask.
All right, I'll take another question from the chat. Julie had to leave a little early, but her question was, would you consider prototyping and exploratory programming as valid ways to gain insight, open questions, and to gain knowledge and insight before committing to an implementation? Or do you expect other artifacts to be generated first?
Oh, yeah. So just to answer that question, if you were to do some history on software development methodologies around the time that extreme programming and agile software development, this lightweight approach was in the incubator, and people was thinking about doing it. We had a couple things that was in the oven. The notion of rapid application development, rapid application prototyping was a thing, and something called the computer maturity matrix, the CMM, was a thing. And that was coming into its own, and rapid prototyping or prototypes is a standard part of heavyweight spiral and even waterfall model software development models. But what the business owners or the end users and some of the developers did not like about the rapid prototypes was that the function of a rapid prototype was just to answer questions and to help you identify and clarify requirements and identify and clarify consequences. and the understood fate of the prototype was you throw it away once you're done. You do not take that prototype and then move it to production. The lightweight people didn't like that. A lot of the business folks, hey, once this prototype is running, it looks pretty good to me. Hey, why can't we go with this? Why do we have to throw it away and then start? There were people who didn't like that. And the Agile community seized on that aspect. And so part of the original Agile group was like, well, let's take these prototypes. And what we can do is just continually improve them. We can add to them as we go along. We can, if you can't fix it, feature it. This could be a way to make the customer happy. And so that it ended up becoming an entire industry when actually it's a pretty good tool to use for prototyping. But I would go further than just rapid prototyping, because what a lot of that rapid prototyping was doing was just developing a prototype of that system and not prototyping how that system performed within the context of the systems that it was going to be embedded in. And so I would advocate embedded prototypes, where the system is a part of a bigger simulation and you can simulate and see how that system is going to be performed in the context of the other systems that it's in that it is being embedded in. That's a better type of prototyping before you get to actually writing production code. That way you can you'll see the impact. Those kind of prototypes are more expensive. They require more effort. They require a greater amount of integration between the subsystems and the ecosystems they're involved with. But they can answer the questions if the subsystems for, let's say, the Affordable Care Act or the Michigan debacle or the predictive policing or the thing that happened in with the Dutch. If that stuff had seen simulation, really embedded simulation modeling, you'd have answered some of those fairness type scenarios up front. So yeah, I'm a big proponent of prototypes and even a bigger proponent of embedded simulation prototypes. But that was part of my talk as well. That kind of stuff requires a serious math background, and I'm not going to sugarcoat it. Even if you have really nice tools to use and you don't have to pull out the calculator yourself to do the math, you still have to understand the concepts. And you don't get those concepts, you aren't born knowing that stuff. So you don't have to get that formal math background either in a formal education. You could do it on YouTube, they're really, really good sources, but you got to get that knowledge from somewhere. It's not optional to not have that. You really cannot guarantee the quality, the reliability, or applicability of any computer system without a fairly solid math background. And I'm not saying that from an educator point of view. I am saying that from writing and failing at lots of code, delivering successful systems, delivering failed systems, shooting myself in the foot, just the whole gamut. If I could recommend one set of things to developers and engineers today, it would be to beef up that math vocabulary in a serious way. I would recommend, with respect to, this is connected to prototyping, many notions of numerical analysis are involved in prototyping, statistical analysis, matrix linear algebra is in there, model theory is in there, category theory is in there. I hate to, and actually I don't hate to, I'm actually happy to let folks know that, there's about, 5 or 6 areas of mathematics that you really should have at least be conversational, be conversant in some of the concepts of those things, even to use the tools. You can't do reliable, fair, equitable, safe software otherwise. It's just not possible. And anyone that is trying to sell some kind of development methodology that somehow lets you go get past the mathematics, that's snake oil. Computers are machines. They operate off of discrete structures. They operate off of mathematical objects. And before any process or policy or idea goes down, those things have to be translated into mathematical objects and discrete structures. That's just a fact of how those things work. We can put all kinds of tools on the front of that to make it appear to be easier and softer. But at the end of the day, this stuff gets translated, and somebody's got to understand it somewhere. And those software engineers and developers are developing mission critical stuff, even at the prototype level. They need to have the requisite vocabulary, and you're only going to get that through a formal education. I'm not saying that you have to find some university. You can get a formal education on your own some kind of way, but you got to get that formal education. Thanks for that question.
And we only have time for one last question, and then any other questions that we have here, we'll present that to Cameron, and he'll send that to you by email. We'll get in contact with you with that answer. But the last question is from Frank Caruso. His question is, do you think that outsourcing to different countries played a role in the programming community problems?
Oh, no doubt did it play a role. And I saw that up close at several places where I was actually employed at. First of all, you simply have, if we're not, you already have the notion of communication being an issue if you have a local team. When you have a scenario where you have disparate cultures involved, different ethnotricities involved, the models, the scenarios, the situations, and this is what I want to say this and really try to bring this point home. Every computer program, every piece of software is a part of some situation or some scenario. That's just what it is. It's a part of a scenario. It exists as a part of a scenario. And that scenario exists inside of some kind of cultural context. When you have a situation where you are developing a system that runs in one cultural context, being developed by people from another cultural context, who often speak different languages and are in different time zones, you are asking for a disaster. And to my knowledge, I can just, every one of those systems that's been developed, you would be able to characterize them as partially successful. There's just not been any of those that you can just walk away and say, hey, this thing was a home run. You just don't have those. There were just crazy stuff happening at every level. And a lot of that just simply has to do with the logistics of communication, but also with the translation of scenarios and situations. People thinking different, not only formal languages that the computer executes, but they think in different languages based off of the culture that they're from. And you translate things like requirements, requests, and specifications. You think about those things in the language, in your natural language. And in many, many cases, the natural language between what's happening in country A and how something is seen in country B, those things aren't equivalent. And so you're going to have a problem at that level. And then you definitely have a problem with our ability to understand mathematics in the United States. One of the groups that measure our literacy rates, United States, in 2015, they rated United States as 38th out of 71 countries. And so in some cases, we're dealing with countries that have much better, command of mathematics than we do. So there's just been a mismatch all the way around. It's not the kind of thing that you can do. And then the development process itself is just not standardized worldwide. And so everybody has their own version of this, that, or the other thing, which is another reason why, if we're ever going to get to regulation and, and any kind of licensing, we got to get to a standard body of knowledge and something that is recognized, around the world. And, that starts with math, a good math background. Again, I'm not saying that from an academic or educator point of view. I'm saying that from the point of view of when I look back at systems that I've been involved with that are reliable and accurate and secure and robust, those systems have a strong mathematical underpinning. And all of the ones that are, to the contrary of that, opposite of that, those are the ones that did not have a good mathematics infrastructure there. So for those folks that are out there that are listening, that might hear this at some future date, because I think this is going to go on the web. If you're considering being a software engineer, a computer programmer, someone who develops software that's going to be used in a public context, please do yourself the favor and the public the favor of having and get a solid math background, bachelor, minor in math at the very minimum, or the equivalent knowledge, a bachelor's in math if you can. I just wish I'd had more. Thank you for that question, Frank.
All right, thank you, Cameron. Thank you for such a wonderful presentation and for the Q&A. I'd like to thank everybody for coming out this evening. And James, do you have anything to add?
No, I mean, that was a great presentation. Thank you, Cameron. Thank you, Trevor, for the introduction. And looking forward to the Free Software Foundation talk that I mentioned.
Okay, thank you a lot. All right, everybody, have a good evening. If you have to travel, be safe. And we will continue this in the fall and September. We will contact you and make sure we are working on the website for it at George Mason, but you will see these. You can go back and see these videos or these presentations, which will be posted on NeoACM as well.